Chapter 3, Section 6 deals with rational numbers. This is the first lesson in this chapter that we're going to be using the textbooks lessons on instead of the ones I built for my previous classes. I just like those lessons better for the material we were using before. The lesson goal is students will identify terminating and repeating decimals and use long division to convert rational numbers in decimals. The suggested pacing says we should knock this one out in a single day, so you can expect homework after the videos today. Of course, you need to start off by writing 3-6 rational numbers. In baseball, a batting average is a ratio of the number of times, the number of hits a player has to the number of times at bat. It is typically written as a decimal rounded to the nearest thousands. The player's batting average changes throughout the season as his number of hits and bats changes. Select a baseball card to see the player's career statistics. So we're going to flip the card over, and there's all the statistics for his various years of playing. People who are really big in baseball, they keep hardcore look on those stats, and they can actually tell you the different years for each player and what their numbers were for that year. Pretty impressive. I have trouble telling you what I had for breakfast today. Now suppose a player hits 32 hits out of 60 times his bat. How can you find the batting average written as a decimal? These are the things we're going to learn in our lesson today. A rational number, when I write this down, this is going to be on your vocab quiz. A rational number is any number that can be written in the form a divided by b, where a and b are integers and b is not equal to 0. Simply put, it can be written as a fraction. It's going to be a rational number. If it cannot be written as a fraction, it is an irrational number. Excuse me. For an irrational number, the easiest way to tell if it's irrational, if it is a non-terminating, non-repeating decimal, it's irrational. If it's not a non-terminating, non-repeating decimal, it's going to be rational, unless it's imaginary, but we're just not worrying about imaginary numbers or undefined numbers right now. So let's see, negative 15, you can write negative 15 as negative 15 over 1. It's rational. Negative 8/10, you can write as negative 8 over 10, negative 8/10. It's rational. Negative 1 over 8, it's already written as a fraction, so yep, it's rational. 28%, that's going to be 28 over 100. It's rational. If you can write the number as a fraction, it's going to be a rational number. Is negative 5 over 6 going to be the same as negative 5 over a positive 6 or 5 over negative 6? Yes, it is. Negative divided by positive is a negative. Positive divided by negative is a negative. It is indeed going to be the same thing. So what are the patterns in decimal form of a rational number? Let's take a look at what they gave us to do that, learn that with. So the instructions tell us to change the fraction to be a negative 1/3 and see how it changes the color. So let's figure out how to use this one. Hold on. This is actually a pretty cool tool. When we change our numbers here, it's going to give us patterns. It's going to show us repeating patterns in the color, or sort of not repeating patterns in the colors to help us determine if it's going to be rational or irrational. So let's get started. We're going to take this one right here, and the number we want is 1 over 3, so we're going to leave that one there. This one is going to become a 3, and we actually need a negative sign in there someplace, so let's do a negative 1/3 is negative 1 over 3, and what do you see? You've got a solid pattern of infinite numbers, and we can increase or decrease our decimal spaces, and you always get the same exact pattern. Since you have the same exact pattern, it's going to be a rational number. Now we're going to set it for 1 over 7. So we have 1 over 7, and yep, that should do it. And look at all those pretty rainbows. Do you see a pattern in the colors? Orange, green, yellow, pink, blue, purple. Orange, green, yellow, pink, blue, purple. I do see a pattern in the colors, and if you take a look, you get the same exact pattern. Oop, where was right there? No, that kind of actually lined it up pretty cool. You get the same exact patterns over and over again of orange, green, yellow, purple, blue, other purple, and then right back to the orange again. And because there is a repeating pattern going on here, it's going to be a rational number. If it terminates or if it repeats, it's rational. If it doesn't, it's irrational. And here's the fact, it got written as a fraction. If we can write it as a fraction, it's rational, simply put. Now the instructions say enter at least 5 new fractions into the color calculator and try to find fractions that eventually repeat zeros as well as those that repeat non-zero digits. Record the pattern. So they've got the 1 over 4 here. 2 of them that they want us to really look at is going to be 1 over 11. So let's change that to 11. And you can see that becomes a repeating pattern of 0, 9, 0, 9, 0, 9. We can drag it out like this, and it's going to be the same pattern every single time. Pretty cool stuff. And they also said 1 over 81. So let's put in an 81 there, hit enter. Woo, look at that rainbow of colors we have here. Let's see if we can figure out a way to line them up like we did the others. And there's a little bit right there. Boom. There's your repeating pattern. You can see it has the same exact pattern every single time, and that means that this is going to be a rational number. If it terminates or if it repeats, it's going to be a rational number. Now what about the fractional version of pi? Because pi is an irrational number, and we have a fractional version of pi that says 22 over 7 and 23 over 7, and I guess that it can't do improper fractions. That's so sad. I was just looking forward to that. So let's do 3 over 7 instead. And 3 over 7, can we find the repeating pattern right here? Oh, there it was. There's the repeating pattern. Every single time you get the same exact numbers. So what do we know? We've got 3 different types of fractions we're looking here that all become rational numbers. If it terminates 0.25, it's going to be a rational number. If it has a constant repeating number, 0.3 repeating, it's going to be a rational number. And finally, if it has a repeating pattern in it, like we saw in this one, it's going to be a rational number. Any of these we knew going in, though, would be a rational number because they were all written as a fraction. If you can write it as a fraction, it is a rational number. Now the textbook wants us to identify these fractions as repeating zeros or non-zero digits. So 1/2 becomes 0.5, also known as 0.50000, and so on. 1/3, that becomes 1.33333, that's going to be that one. 1/5, that becomes 0.20000. I know 1/10 becomes 0.1000, and 1/20 is going to be 0.50000. The rest of these, okay, that's going to be 0.05000 for that one. The rest of these I'm not so sure about. So let's take and find if we have an open calculator here. We do. We're going to do 1 divided by 6, and what does that give us? That gives us repeating non-zero digits of 6. And then 1 divided by 15, that's going to end up giving us repeating non-zero digits of 6. Now that last one's a 7 because they rounded up. So that's going to go here, that's going to go here. And the last one we need is 1 divided by 32. And that one, that terminated, that means that after that 5, you're going to have a whole bunch of zeros going on. And with that, all of our answers are going to be correct. Now the textbook wanted you to look at the denominators in each of these fractions and come up with a pattern, see what they all have in common, and that's something pretty hard to just jump out and see and figure out. But what they wanted you to realize is that when you divide the decimals, that all the decimal numbers that ended in 0, if you prime factor them, they're only going to contain 2s and 5s. That's it. Prime factorization of 2 is 2, 5 is 5, 10 is 2 times 5, 20 is 2 times 2 times 5, and 32, that's 2 times 2 times 2 times 2, so that's 4 2's. If they factor down to only contain 2 and 5's in the denominator, then they're going to be a terminating decimal, or something that constantly repeats zeros at the end. And now it's time for us to pick up a few vocabulary terms here. Any fraction can be expressed as a decimal by dividing the numerator by the denominator. The decimal form of a rational number is called a repeating decimal. A repeating decimal can be represented using bar notation. In bar notation, a bar is drawn over the digits it repeat. Now these are things that you've already done in elementary school before, but it may be the first time you truly define them. So drag the slider and see the decimals using bar notation. So if we took the slider and come this way, that means that 0.44 repeating is going to just become 0.4 with a line over it, and then 2.4343 whatever repeating becomes 2.43 with a line over both the 4 and the 3. Now we get to drag and match each one of these up. So 0.1 repeating, a bar is going to be over the 1. This one, you have 0.61, but the 1 is the only thing repeating. It's going to become that one. This one here, both the 6 and the 1 repeat. That's going to go there. Next, you have 0.6000, so the 0 is your repeating number, but in reality, we wouldn't write it that way. We would just write 6.16 and we'd stop. We wouldn't put the 0 with a bar over it. That's kind of silly, and that means the last one must go down here where you have 161, 161, 161 as your repeating numbers. It made it sound like we got it wrong, but it gave us all right, so I think the computer's confused. We also have terminating decimals. Every decimal is a repeating decimal, and decimals that repeat with a digit of 0 are called terminating decimals. So like that one we looked at earlier where they had the bar over the 0 saying the 0 was the only thing repeating, that's going to be a terminating decimal. You can see they demonstrated that here at 0.25. 0 with a bar just became 0.25. Now the instructions want us to write 1 over 40 as a decimal. Determine if the decimal is going to be terminating or repeating. And can you predict whether it's going to be terminating or repeating? Yes, you can, because if you were to factor out 40, you'd get 2 times 2 times 2 times 5. That's only 2's and 5's, which tells you this is indeed going to be a terminating decimal. Now the textbook shows using long division to do this, and you should know how to do this by now. You are an accelerated class, so you should be able to do the long division and understand what happens here. First number went in the house, which was 1. They divided by the second number, 40, and they got them 0.250, and the 0 became a repeating pattern, and you would actually write that final answer as you see it right here, 0.025. That's all there is to doing these. Really simple stuff here. On the part B, it says determine if the decimal is terminating decimal. Well, you reach the point that all you have is zeros repeating, and since you have zeros repeating, it is a terminating decimal because we don't really count those zeros. Now it's going to be your turn. Pause the video and work this problem on your own. See if you can get it right. First off, just looking at it, is it going to repeat or is it going to terminate? 8 is 2 times 2 times 2. All you have is 2's. That means it's going to terminate. And when you do your long division, you should get 0.375 as a terminating decimal, and that checks. And then determine whether it's terminating or repeating. It is going to be terminating. That checks too. Easy math. You could be able to guess that one before ever actually solving the problem. So let's take it a little further. How about a negative number such as -5/6 as a decimal? Determine whether it's terminating or repeating. Well, what is 6 factored out? It's 2 times 3. So 2 times 3 is not 2 and a 5. That means that this is going to be a non-terminating decimal. It's going to go on, and you're going to have a repeating pattern involved here because it is written as a fraction. So using long division here, they divided it out and they got negative 0.333, and the 3's just kept right on repeating. So you do indeed have a repeating pattern. When you write it out, you just put a bar over your 3 for bar notation, and then you would say that it is indeed going to be a terminating decimal. I totally missed that one out. It's a non-terminating decimal. I was talking and not thinking. It's non-terminating because it does have a repeating pattern. If the fraction is negative, how will it affect when it's written in decimal form? Won't make any difference at all. Negative fraction becomes a negative decimal. That's all there is to it. Now it's going to be your turn. Pause the video, solve the problem, determine whether it's going to be terminating or non-terminating, and which one of those is going to be the correct answer. Go ahead and do that right now. Alright, when I worked it, I set the first number in the house, and I went ahead and put the negative sign with the first. In the end, it makes no difference where you put it. So the first number, negative 3, went in the house. The bottom number, that's outside the house. 11 goes into 3, 0 times, and that don't even worry about the negative sign right now. Annex in your decimal and your 0. 11 goes into 30, 2 times, which is going to give me 22. Subtract that out. I'm going to get an 8 left over. I'm going to annex in a 0, and I'm going to bring that down. 11 goes into 80. How many times? That's going to be 7, which is 77. Subtract that out, and hey, we get a 3 here. Bring that down. We get right back to our 30. 11 goes into 30 2 times, which is 22, with 8 left over. We'll annex in another 0 and bring it down. 11 goes into 80 7 times, which is 77, with 3 left over. And so we have that repeating pattern, which we would write as 0.27, and the repeating bar, the bar notation, goes over the 2 and the 7. So which one of these is going to be the correct answer? It is going to be D, and I did forget to go and add my negative sign here because a positive divided by a negative is going to be a negative. And so from there, I can say it is going to be negative 0.27 repeating. And then is it a terminating or repeating decimal? It is not terminating. It is, however, repeating. I think this is going to be a good spot to stop for this lesson. We will come back for part 2 here in just a minute.